Now, what I need to do is I need to measure temperature, and more specifically, I need to measure temperature in a way that I can put into a computer, a PLC. So, an electrical way of measuring temperature. And probably the easiest electrical method of measuring temperature is just to measure the resistance in a piece of wire. Because hopefully you realize that when you heat up a piece of wire, the resistance changes. In fact, there's a relationship between resistance, voltage, and current. I don't know if any of you have ever seen it before. It's V equals I R. So if I put a voltage across a piece of wire and I measure the current, then as the piece of wire heats up, the current should decrease because the resistance increases. This is a very simple way of measuring temperature. Now, we need to do this a little bit more precisely than just getting a piece of wire. So what we do is we get a very precise piece of wire, which is made of platinum. And platinum has the chemical symbol PT. And we get this piece of platinum, and we say that we make it precisely so that it's 100 ohms at 0 degrees C. Now, if we have this thing, it's 100 ohms at 0 degrees C. Anything above 0 degrees C, and the resistance goes up. So all we need to do now is measure the resistance, and we've got it. We make these, and they're called, because it's 100 ohms at 0 degrees C, because it's made of platinum, we call it a PT 100. Now, sometimes we use resistance devices which are, say, 500 ohms at 0 degrees C. What do you reckon they would call something that's 500 ohms at 0 degrees C? You're right on top of that. Yep, a PT 500. And if it's 1000 ohms at 0 degrees C, it's a PT 1000. So we have PT 100s. Now we have this thing called the alpha. All of these things are 100 ohms at 0 degrees C. But unfortunately, the rate at which the resistance increases with temperature slightly varies. There's the DIN standard, where it increases by 0.003850, the American standard, where it increases 3811, and the international standard. Now, I'm just coming to your question, Julian. It is pretty linear. It's pretty linear. In fact, here's the graph. If you look at the graph, it's what you would say is it's linear-ish. It's linear enough. So this is with alpha of 0.00385. If we looked at, which is the one we normally use, the international standard, the American standard, 0.00381, would probably be just a little bit different than that, just a little bit below it. Truth be told, you probably wouldn't even notice. Here's the actual equation, and although, I don't want to go into technical details, although it's a cubic polynomial, it's effectively, alpha is the linear term, which is the important term. So, it's, to all intents and purposes, linear. Unfortunately, I don't know of any identification method they have, so that if you pulled a PT 100 out of the cupboard, I don't know of any method for identifying one from another. What I'm trying to say is, if you pull a PT 100 out of the cupboard, you need to have the bit of paper that came with it. If you haven't got the bit of paper that came with it, the only thing you can really do is warm it up to 100 degrees C, work out what it, or measure its resistance, and then go to the different tables and see which one you've got. That's really all you can do. It's not like they're color-coded or anything like that. They're all slightly, you know, they all look pretty well the same. In fact, this is what they look like. Now, before we get to this, I just want to do, here's the problem with a PT100. I've got a resistor just here. I've got some cables coming out of that. I've got a red cable, and I've got a white cable. Now, I'm not going to be able to draw white. I'll draw, oh, yellow doesn't show. I'll draw grey. Okay. Now, what I'm measuring is, I'm measuring round about, this thing has got a resistance 100 ohms, it's supposed to be an ohm, at 0 degrees C. 100 ohms at 0 degrees C. Now, the problem I have is that if these leads are any length at all, say I've got 20 meters of lead there, then I'm going to start picking up quite a bit of resistance in the leads. Also, these leads are going to be subject to things like heating. So the resistance of those leads will change with heating. I don't want to measure the resistance of the lead, I want to measure the resistance of the PT100. So I've got a slight problem. Now, before we go on, Russell says that you can identify what type of PT100 you have because it has a sticker on the side. That's nice. I pulled one out of the cupboard the other day and there was no sticker. So, yeah, if it's got a sticker or a piece of paper, you're sorted. Now, with a standard PT100, a 2-wire PT100, such as this one, when you measure the resistance from here to here, you're also measuring the resistance of the leads, and that's going to give you a false reading. What we do is we have either a 3-wire or a 4-wire PT100. With a 3-wire PT100, what we would do is we would measure the resistance across the 2 red wires. And the resistance across the 2 red wires should give us an indication of the resistance in the leads. The 4-wire is even more accurate because we measure the resistance across the 2 red wires and we measure the resistance across the 2 white wires. And then we can be sure that we're eliminating the resistance in the leads. There is another type of 4-wire, and the other type of 4-wire uses what's called a blind. And the 4-wire with a blind, you have a red lead, you have a white lead, and then you have 2 blue leads. And the blue leads simply go up, join together, and come back in what's called a blind. The idea is if you measure the resistance in the blue wires, it should give you an indication of the resistance in the leads. According to TAFE, we're supposed to wire these things up using a thing called the Wheatstone bridge. Let me just write that down. Wheatstone bridge. This is a Wheatstone bridge. And this, I'll just go through how a Wheatstone bridge works. If I've got 12 volts there, so that's plus 12 volts, that's return on that leg. Now, if I have 12 volts at this point here, I should have 12 volts at that point there. If let me write this down. R2 is the same size as R3. How many volts do I have at this point here? Very quick off the mark. Yes, at this point here, I have got 6 volts. Now, if R1 is the same resistance as the resistance element, as the PT100, how many volts do I have at this point here? You're absolutely right. I've also got 6 volts here, which means that across the output, I've got 6 volts on one side and 6 volts on the other side. I have no volts across the output. Now, if I was to heat this up so that let's have a think. What's going to be easy numbers? So that if this was R1 is 100 ohms, and I heat this resistance element up a lot, so that it becomes say 200 ohms. How many volts do I have at this point here? Okay, I've got 12 volts here. I've got 0 volts here. And I'm dividing that across 300 ohms. Yay. So what I end up then is 9 volts just there. So I've got 9 volts there, I have 6 volts there, I get 3 volts on my output. That's how a Wheatstone bridge is supposed to work. Now, straight away, this does bring up one important point. I'm actually passing voltage. I've got voltage across my resistive element. I'm passing current through my resistive element. If I'm passing current through this, what's it going to do? Yay, it's going to get hot, it's going to heat up. Now that is a big problem. It's called self-heating. The act of actually putting current through the resistance will heat it up and give us a false reading. For that reason, we try and only put a tiny current through the thing. Now, when we're using Wheatstone bridges like this, we've got different ways of wiring different bridges for different types of RTD. If we have a 2-wire RTD, we wire it like this. A 3-wire, we wire it like this. A 2-wire with a blind, so it's a 4-wire, we wire it like this. A 4-wire, we wire like this. Now, let's be realistic about this. You don't go out and buy your $200 PT100 RTD and then nick out and buy a couple of resistors and start wiring up a resistor panel. You don't actually do that. What you actually do is you just connect it to the appropriate terminals on the PLC. So in reality, what you're going to have is you're going to have a bunch of screws, and you're going to have your PT100, and you're going to connect the 2 reds up to that, and you're going to connect the 2 greys up to that, and your PT100 will be just there. And then you go to your PLC and you program it and tell it you've got a 4-wire sensor and the 2 reds are on 1 and 2 and the 2 greys are on 3 and 4. There's no Wheatstone bridges involved. But it's nice to know about Wheatstone bridges. These are the sort of things, the sort of packages that PT100s come in. You get different, most things come in a probe type package. A probe type package looks like this. When you're ordering probe type packages, it's important that you get the correct length. We'll speak about that more when we talk about thermo wells. Surface mounted ones, that's really useful. If you need to measure the temperature in, say, a piece of pipe, and you don't want to drill a hole in the piece of pipe and stick an element in, what you can do is just glue a surface mounted temperature sensor to the outside of the pipe, and you get a pretty good reading if it's a metal pipe.